Hi y'all, my name is Chris Stone, and this is my final presentation for MEGN566, combustion. This is a lecture on shock waves, flame propagation, that kind of thing, and it is designed for an upper level class in high school, maybe a senior level combustion class, if that kind of thing is offered. Anyway, a quick note on safety for the demonstration. The demonstration was performed with professionals who understood the systems being used. The demonstration was performed in a safe environment, and a fire watch was conducted post-test to ensure nothing had ignited and could cause a hazard. And with that, let's get into it. Hi y'all, my name is Chris Stone, and I have an undergraduate degree in mechanical engineering from the Colorado School of Mines. I also am in a master's program at the Colorado School of Mines, also for mechanical engineering. And I'm here to teach a quick lecture on flame propagation for a high school combustion class. The structure of this is I will show a demo that I designed, built, and executed, and then we'll talk a little bit about the theory and go into some of the calculations behind it, some of the assumptions, and showing how to compare a combustion demonstration to some first principle theories in a very high level overview. Anyway, let's dive in. All right, let's jump into some of the learning outcomes of this lecture. First, we're going to go over the difference between a sound wave, a deflagration, and a detonation. Then we're going to talk a little bit about forms of energy. This should be a little bit of a review, but from a combustion-themed perspective. And then we're going to talk about flame front propagation, and finally shock tubes. And you'll see why that's important here in a second. So, for the demonstration, please watch the video attached, and it'll be just inserted here right after I stop talking. Note that this was a very quick and dirty demonstration, and doing a more instrumented and accurate system may yield significantly better results. Anyway, enjoy.
So you have lighting.
Oh, perfect. Anyway. Hi. What is up? This is my demonstration for the MEGN566 project. It is a plasma popper. It's something I threw together at Home Depot for 60 bucks in 2 hours. It is currently zip tied to a Nerf gun, but it consists of a MAP gas torch, a run of 3/4 inch pipe, about 10.5 feet, into 2 Gatorade bottles that are typed together end to end. This is going to be a chamber that fills with gas as well as propagates the flame, and this is our resonator chamber that actually emits most of the sound from this. I will fill this chamber with gas as well as the tubing and allow a flame to propagate around it into this chamber and out the end, creating a pop and a bit of a ball of fire. This demonstration will show flame propagation in an enclosed environment and simulates a shock tube. Demonstration, about 10 seconds of gas. Hell yeah. All right, here we go.
There it is. Yep. Jesus Christ.
All right, I hope you enjoyed that demonstration. It wasn't too unprofessional for you, so here we go into theory. So, movement of energy. First, let's talk about sound waves. So, sound waves are basically a compression or a rarefication where a sound or a wave is propagated in an elastic medium. This medium could be air, it could be any sort of gas, it can even be the ground. If you've ever felt subwoofers that really shake things, that's kind of propagating that energy through a wave through the ground, which is technically an elastic medium. But normally we think of it in air as a wave that is traveling through that air. Now, we can talk a little bit about plasma. Plasma, force state of matter, all that kind of thing. All you got to know is it's really hot, and plasma can be created most notably by electrical energy. When it arcs, you are superheating the air in between whatever electrodes are creating that arc, and you get a very, very hot bolt between the 2 points. You'll see why that's important here in a sec if you noticed how the igniter on the demonstration worked. And of course, a detonation, you've seen explosives before, I'm sure, either in movies or in real life, and it creates a massive amount of energy release, as well as a sound wave, as well as shock wave. So you can kind of see in this photo here, this edge, that is the shock wave that is traveling through the air at a supersonic speed. And that can cause a massive pressure fluctuation at this boundary here, which is what a massive part of the destructive capabilities of an explosion are. Not so much the fire or the atomization of some of the materials around you, but this shock wave is what causes the most damage in an explosive. Now, we got a deflagration. Now, this is where the demonstration comes in. Remember, we have a tube, and we have a flame front traveling down that tube. It's not going supersonic. It's not breaking any sound barriers. It's not creating any shock waves. And yet you hear a sound at the end. And so you see the flame go around the tube, around and around, and then out into the 2 chambers. You have your sort of fuel reservoir expansion chamber, which is that first Gatorade bottle. Then you have your second chamber, which is the resonant chamber, which kind of creates more of the sound. And we'll get into that here in a sec. But mainly what you need to know is the deflagration is what we're going to be modeling when we talk about the demonstration and how we use the plasma popper to propagate a flame around that tube and then into that other chamber, causing a larger explosion out of it. So it goes from a deflagration into an explosion. So to recap forms of energy here, we have electrical energy, where you have a voltage potential between 2 points. Usually they have to be conductive to make this work. And when you have enough of a potential between the two, so enough voltage, if you want to think about it that way, you will then cause an arc. An arc just means that there's enough energy in between those 2 electrodes to jump the electrical current between the 2 of them and basically break through the electrical resistance of whatever medium is in between the 2. In most cases, that's like air or some inert gas, but in our case, it's air. And so inside that torch head, you have a very small like voltage generator. When you press the button, it makes that clicking sound, that spark. Same thing that exists on barbecues, stoves, all that kind of thing. And so when you create that large potential gap between wherever the electrode from the voltage generators and then the outer casing of the torch head, which is your ground, there will be a spark that jumps between the 2. And that spark is essentially plasma inside of there. So it's superheating the air in between those 2 points, which then allows thermal energy to be released from the chemical reaction. So the air and the fuel in the tube are sitting there. There's nothing to bring an explosion or a combustion or anything out of the until we have added in that energy from the plasma, which then sets off the chain reaction of fire propagating down that tube. So the way that this system works, you have your electrical energy coming from the little igniter, the spark, the voltage generator, which turns into a plasma between the 2 electrodes. And that turns into chemical energy and thermal energy as it is released down the pipe. And then once it reaches that gas chamber at the end, it starts turning into mechanical energy. So it'll release a lot of thermal energy, which releases a lot of expansion of the air and fuel mixture, which then is forced into that smaller opening, which is the lid of the Gatorade bottle, into the other Gatorade bottle, and then it's allowed to expand again. As it expands out of there, it will very, very, very slightly break the sound barrier, and you'll hear it's mostly a pop, but sometimes if you get enough gas in there, it'll make a really, really, really loud bang, and then that is a shock wave that's coming out of that second Gatorade bottle with the end cut off of it. And so you turn your electrical energy into mechanical energy after transmitting the chemical energy down the pipe out into the secondary chamber. Okay, let's keep going. Here's a bit of math. Now, to fully understand these equations, you will need a 4-year degree in a technical field from a solid university and 2 to 3 years of graduate work to truly understand this. That's both classwork as well as lab work to really get this. So, what are all these symbols and what are they telling us? So a lot of these symbols are some inherent properties of the fuel and the combustion reaction, as well as the oxidizer, usually air. But if you look at that bottom sort of equation I put down, the SL, so SL is your flame speed, you're going to have the energy released and the delivery power of that energy, so how it can propagate, and then the thermal inertia of the medium it's going through, as well as the energy resistance. So that's what literally all of these numbers mean up here. They are literally just telling you, okay, cool, the fuel is able to burn and propagate with this much force, and there's this much force resisting that. How fast can the flame go? And if this number's 0, or sometimes if you set up your calculation on it can be negative, obviously it will not propagate. But if it's within a valid range, and this is a positive number, these will allow you to model that flame speed in a laminar condition. This is laminar flame speed. Noting that this is for laminar flame approximations, you cannot account for turbulent ones. Please let me know after class if you don't know what laminar versus turbulent is. I'm going to have to do for this sake of time. Okay, we breezed over these, but basically continuity and Navier-Stokes are the momentum of a fluid, and these are used kind of as factors to influence the flame speed on a more granular level, with accounting for viscosities, accounting for any forces external, as well as forcing mass to be conserved. So, with this whole flame speed equation, we can give an estimation of what the flame speed in that tube theoretically should be. If you are trying to model a more complicated flame, like a turbulent flame, you're going to require something called CFD, or computational fluid dynamics, and that basically takes a lot of computing power and gives you fairly accurate results for very complicated systems. Though, again, the same applies for both the laminar model and the CFD modeling. You are going to have a model that is only as good as the assumptions that you put into that model. So, this over here, this figure kind of shows a laminar flame as it travels through a tube. So this nice curve, that's what it will look like in a tube, and then slowly getting more turbulent. So this is a turbulent flame in the tube, and it will propagate, look somewhat like that as it goes along. Now, based on the demonstration, what do you think the flame front was before I show you any math in the demo? Was it laminar or was it turbulent? Okay, I really hope that you picked turbulent, but we'll get into that in a sec. Okay, so quick recap into how the demonstration was functioning and how we're going to kind of analyze it as a shock tube. Shock tubes are a very standard piece of equipment in combustion and general engineering practices when it comes to doing any kinetics work or any reaction rate work with combustibles. So there's a lot of data out there, a lot of models out there that we can use, pull to try to validate our model. So first off, you have your igniter and your driven section. This is where the gas is, and this is where your igniter is, and that corresponds to this driving section of the shock tube. Driven section would be this entire tube, and arguably getting into this first combustion chamber here. So that's where the flame's going to propagate through. Now, this diaphragm media, which is usually used for the pressure transducer, is usually a diaphragm media to help keep your pressures constant and keep your flame in the way you want it to. That can be modeled as the sort of pinch point or the convergence of the two Gatorade bottles there. And if we had a pressure transducer, we could put that on there and get real-time pressure data for what's going on inside that chamber. And then finally, we have our either combustion chamber, and that would be the resonant chamber on the device. So this resonant chamber forces the gas to expand rapidly and would generate the shock, hence shock 2. Cool. Now, To model my shock tube, I am using a Python coding plugin called Cantera. It's developed by a cross-functional team from Cal Poly and Mines and a few other institutions, and it can simulate a shock tube. It can simulate a flow of gas and then an ignition and a flame through that shock tube. And so with this code, I can estimate the amount of time it takes for the flame to go 10.5 feet in 3/4 inch tubing. So I did that calculation, and then I measured in real time what actually happened during the videos that I took. So again, for our laminar approximation, using that code, we got a time of 6.45 seconds, which is very much so on par with a propane-like, methane-like gas going at a equivalence ratio of 1 and a high speed through the tube. And then in the second figure here, I got 1.88 seconds for my demonstration, which is like 3 times faster. So why is this? Why does this happen? The answer is based on our assumptions. So when I'm using my Cantera code, I'm assuming a laminar flame because I'm trying to model this using first principles and not CFD, which would be probably a more accurate and significantly better method to model this system. So for that, the flame is capped at a maximum speed, and anything above that has to introduce any sort of either flow differences, like there's a medium that's flowing through the tube, so the flame speed and medium speed have to be added together, or it can be a turbulent flame. Turbulent flames can move significantly faster than laminar ones. So that is my best guess of what's happening in here. If you look at the shape of the demonstration versus that chart I put up a few slides ago, the flame front looks significantly more like the turbulent flame than the laminar one. So that was the big assumption we made that probably threw these numbers way off. And once you know that, you could add in a fudge factor to say, hey, my data says this, but my code says this. If I just add this little factor, and if your factor is either linear or exponential, you can model that and give yourself an empirically derived model of the exact experiment, and then use that to predict other similar environments. And that can be a valid method, but for something like this, CFD would be the proper tool to use. Okay. We'll quickly go back into shock tubes here and what they can be kind of used for, because they're very important, and this is one reason I built this model, is to kind of make a mini shock tube as well as show some math behind it. So in chemical kinetic research, you can figure out your K factors and a lot of other data from different reactions by blowing them up and figuring out the pressure and the speed difference of the flame as it goes through the tube and then breaks through into your shock chamber. You can material test some systems. So if you have a diaphragm material or just anything you want to test in an explosive environment, you can put that in between the driven section and the detonation section, and it will then tell you, hey, does this material break? Where does it yield? How does it yield? And can give you a lot of good engineering data on that. You also can obviously figure out some combustion reaction rates, as the rate is specifically tied to your speed and your movement of energy within the shock tube. And then blast wave testing kind of goes with materials testing. If you have a large enough shock tube or an environment that is needing to be tested that you could fit in one, you can then use the shock tube to test the shock wave that is created against whatever system you have in there. Now mine is definitely more of like a standard shock tube where you can put a diaphragm material at the end than a blast wave, but same principles apply. And again, CFD is probably your better move for modeling this kind of a device. Anyway, thank you so much for tuning in. And if you have any questions, please let me know after the lecture. I appreciate it, and have a good one. If you have a laminar flame, so that means I'm gonna have to assume that people know. That's tough. Okay.